quick review for previous class. So in this lecture 4, we try to correlate the diffusion phenomena which we observe in macro scale with the atomic jumping process we observe in micro scale, right? So what's the relationship between them? As you know, the diffusion actually is a result of series of atomic jumping process. So in order to well describe the atomic jumping process, so we know that we estimate the atomic jump rate. The jump rate means the successful jump rate equals to the atomic vibration frequency times the probability of the atoms which can cross the energy barrier. So we know that the atomic successful jump rate along one direction, gamma prime expressed like this, is related with the beta, is a bond strength between atoms, and the reduced mass, which is related to what type of atoms we're dealing with, an energy barrier, and also the temperature. And now we know the gamma prime, right? And actually we want to find an indicator which can help us to correlate the diffusion phenomena and also the atomic jumping process. So here in the beginning, we ask you whether the displacement, the capital R, the average displacement or the total displacement of the diffusing atoms, can this be an indicator? And as you know that it cannot, because if it is random walk, then the capital R, the vector of capital R will be equals to 0. So it turns out it cannot be a good indicator. So here in your textbook, it proposed that the mean square jump distance is a good indicator to describe to link the diffusion phenomena and also atomic jumping process. So next, we try to use this as an indicator to describe the diffusion phenomena. The case we choose here will be the diffusion from a point source. So we try to quantitatively estimate the mean square displacement in this diffusion from point source. So after series deviation, we know that the this will be equals to 60 tau. So you find that the mean square displacement actually is proportion to the diffusivity and also the diffusion time period. And next, we already successfully to link mean square displacement with diffusion phenomena. And next, we use the probability point of view, try to link the mean square displacement with the atomic jumping process. So here, we also, based on this, as long as we know the radial probability of the diffusing atom be found through whole space, then as long as you know P as a function of capital R at time tau, then you can get the mean square displacement. So after, how to do that? So we assume the diffusion is also a result of jumping process, right? So we focus on the one-dimensional case, and we use we calculate the total of combinations of atom at the x equals to 0, jump to x equals to n. So we want to estimate the probability. So after series deviation, we know the radial probability show like this, right? So we take this probability into this equation, and after series deviation calculation, we know the mean square displacement equals to gamma. It's a total jump rate, diffusion time tau, and mean square jump distance, small r, is a jumping distance for the atom. So finally, we get the diffusivity in macro scale equals to total jump rate and the mean square jump distance, right? So this result shows that the diffusivity of the materials can be adjusted or tuned by atomic jump rate and also mean square jump distance in microscale. So these two parameters also is highly related with what type of the atomic diffusion mechanism involved and what kind of material, what kind of crystal structure of your interesting materials. So, which also implying that if you want to increase or decrease the diffusivity of your materials, you can play with either the atomic diffusion mechanism or different types of crystal structure of your materials. So I'm going to give you a quick summary for previous, for section 1. As you know, we got the atomic jump rate related with bond strength, reduced mass, and energy barrier, and also temperature, right? And by using the mean square displacement as an indicator, we successfully to get the expression of diffusivity. So like this is a total jump frequency mean square jump distance divided by 6. But don't forget how we get this. We talk about, we've put more efforts on the random process, right? Random walk process, right? So how about if the diffusion is not a random walk, it's a correlated jumps. For example, that it is a vacancy-mediated diffusion mechanism. How to modify the diffusivity which we derive from previous slide. So that's back to the equation we derived from a previous slide. Mean square displacement can equals to the total number of jumping process of the atom, mean square jump distance, and also the extra turn. But in previous slide, we show here, if it is random walk, then as you know, when you summation the cosine term, you will get 0, right? But if it is not a random walk, it is correlated jumps. So as you know, we have a non-zero term here. So in order to evaluate how correlated jumps it is, so we use a term we call a correlation factor. F is defined as mean square jump distance divided by n tau is a total jump numbers and the mean square jump distance. So based on these equations, we know the mean square jump distance be modified equals to n tau times the mean square jump distance times F times the correlation factor. So as we know, if it is a random walk, the F will be equals to 1. Right? Equals to 1. So this equals to this, and we don't have this term. But if we define the correlation factor F, right? If F not equals to 1, then we can use this F to evaluate how correlated jump it is. So continue, what's the F? If you substitute this mean square jump distance with this term, then you will get 1 plus the extra term. Because it is not a random walk anymore, so this term will be a non-zero term. So I'm going to give you 3 cases which can give you some pictures about the value of F. So the first one is the one you already know. In non-correlated jump or in the random walk process, the F equals to 1. Okay? And there are 2 very extremely cases I'm going to show you, but we don't have chance to see that, right? For example, like for the case 2 is if the jump number I and I plus 1 jumps are identical, What this means? Means, for example, that means the jump always like go to the right-hand side, always go like this way, means the I and I plus 1 jumps are identical all the way to the jump to the right. So under these situations, means the theta equals to 0, right? Because the directions will be the small r, the vector of small r, and the vector of next small r, the r I plus j will be identical. So the theta equals to 0 under these situations. Then we got the capital R dot capital R. Then based on this, compare these two results, we know F will be equals to n tau. But as you know, we don't have chance to observe the atoms always jump all the way to the right, right? It's very difficult to observe this phenomenon, so I call it is a very extremely case. And the other very extremely case would be this jump and next jump are totally opposite. What this means this jump will jump to right hand side, and next jump will be jump to left hand side, and back and forth. Is very difficult. The probability is very low, right? The probability of this case will be very low. But I just want to show you, if under these situations, then you can expect the theta will be what? 180 degrees, right? And based on this, we know the mean square jump distance equals to 0. So under these situations, we know F equals to 0. So now you have some idea about the value of F, right? So in order to allow the mean square jump distance can be also used in random walk and also used in correlated jumps. It can be used in non-correlated and also correlated jumps. So we ended F to modify the mean square jump distance. Based on this idea, if you take a look here, the total deviation in the results we got here, actually the one we don't have the F, right? So this equation can only be used in random walk. In order to explore or allow this equation between the diffusivity and also the mean square jump distance and jump rate, this relationship can be used in correlated and non-correlated jumps. So we try to end it F to modify these results. So we mean square displacement, we ended F to modify this term. So also this mean square displacement are the same, right? So this equals to this. So the diffusivity will be, after modify, then diffusivity will be expressed like this. So we just ended F this correlation factor to modify these results. And some people probably will ask, Professor, gamma, and now you got the Z times the gamma prime. What does means? This equation only be used in random walk, and this equation now can be used in all possible in the non-correlated and correlated jumps, right? Regarding to gamma, as I mentioned, gamma means the total jump rate, right? And gamma prime is a jump rate along one directions. So Z means the possible directions. So you use the possible direction times the jump rate along one direction, you got the total jump rate. Okay, so now Z here, some people also call it as a coordination number. It's a possible jump directions. And the gamma is the one you learned in previous slide. It's a function of beta, reduced mass, energy barrier, and also temperature. Okay, so now give you some ideas related to if the jumping process we deal with is a random walk, then F equals to 1. But if it is an interstitial diffusion mechanism, which means we have atoms or dopants at interstitial site, and this smaller atoms diffuse through interstitial site. So which means let's know it also belongs to non-correlated jumps, right? So F equals to 1. But if the one we deal with is a vacancy-mediated diffusion, then under this case, the F is not going to equals to 1. It probably will locate between 0 to 1. So you can just you don't need to assign F equals to what. You can just put F layer until if I give you some you can check the literature to know the value for F. Okay, so I'm going to end the one more information in the first section. Before we end the first section part, we want to add one additional information here. We put the correlation factor F to allow us to modify the diffusivity as a function of total jump rate, mean square jump distance, and also the F, the correlation factor. So this is the final results you get. So I'm going to show you how to use this equation or these results. But basically, if we take a look on this one, we can know that in order to tune or control the diffusivity of your materials, you can do either change the gamma, small r, or the F. You can play with that, right? So now we move to the second section is the diffusion in crystal lattice. And what this means, actually, we want to show you how the atoms jumps in crystal lattice, in FCC, in BCC, through different diffusion mechanisms. So we are going to introduce 4 different types of or kinds of diffusion mechanism to you. The first one is a ring mechanism, and vacancy mechanism, interstitial mechanism, and also we have interstitial C mechanism. You use a yellow marker to highlight. It's the extra CY is an interstitial C mechanism. And we will accompany with different diffusion mechanism in different types of crystals. Here we focus on the cubic system, including FCC, BCC structures. And in first part, we will the example the material system we introduced to you will be focused on the metal materials. And the second part, we will move to the ionic solid materials. And the mechanism we focus on will be focused on the vacancy mechanism. So let's move to the first part. But don't forget the topic here or the purpose here will be you need to estimate the diffusivity of the diffusing atom in different types of materials through different diffusion mechanism. Okay, so let's move to the first. For the first diffusion mechanism is we call the ring mechanism. What's a ring mechanism? A diffusion atom at substitutional site exchange with a neighboring atom by a cooperated ring-like rotation movement. So what this means, we have the host atom here in black, and we have a diffusing atom in blue. So now the diffusing atom is at the substitutional site or at lattice point. It was going to exchange with the location with the neighboring atom, host atom, to get in the same time. In the same time, this means the diffusion atom is going to move to a right-handed side, and the host atom is going to move to a left-handed side. They move together. So this type of movement, we call it as a cooperative ring-like rotation movement. So under this situation, this kind of diffusion mechanism, you can see before diffusion, the atom was located at here. Then after diffusion, it moved to right-handed side. So this diffusion mechanism, we call the ring mechanism. But don't forget, as you know, this type of movement will need to overcome the high lattice distortion energy, right? Because the atom actually don't have this kind of space, right? They are closely packed in between, right? So if you want to move to here and this atom move to right-handed side, it will for sure will cause the high lattice distortion. It need to push these atoms to up, and this need to push these atoms to down so they can move together, right? So this will cause the high lattice distortion energy. So it is not an energy favorable process. And because the atom need to overcome this high lattice distortion energy, which means the atoms need to have sufficient energy, right? So it easily to observe in high temperature, because in high temperature the atom have higher energy, right? Or you can say that higher percent of atoms can have chance to have higher energy to overcome this distortion energy. But some people probably will ask, Professor, yes, under this situation, the lattice distortion energy will be very high. But how about, are there any chance to decrease the distortion energy? Probably. For example, like 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. These 8 atoms move together. Then probably the distortion energy will be lower. Yes. This is the other option. To lower the distortion energy or distortion degree, then the atom, the more atoms move together, for sure will decrease the distortion degree and distortion energy, but the probability will be very low. Means this atom move to the right-handed side, let's move all the atoms together to move to the right-handed side, the probability will be very low. Okay? So this is the this diffusion mechanism we call it a ring mechanism. And the second one is the famous one we call the vacancy mediated diffusion mechanism. So what this means, we have a host atom in black, and the diffusing atom at the substitutional site or lattice point exchange with the neighboring or nearby vacancy through atomic jumping process. This kind of diffusion mechanism we call it is a vacancy mediated diffusion mechanism. And this mechanism depends on what? Depends on, for sure, there's a vacancy concentration. For sure, you need to have a vacancy nearby. So vacancy concentration will play a very important factor. And also the atomic migration energy need to overcome this energy barrier. So we will say there are two criteria: vacancy concentration and also atomic migration energy. And regarding to the vacancy concentration, which parameter will affect the vacancy concentration? The first thing come up from your mind probably will be the temperature, right? We know that the vacancy concentration will proportion with the exponential to minus vacancy formation energy divided by kT. So if you want to have more vacancy or higher vacancy concentration, then the easy way would be increase the temperature, or the vacancy formation energy you got the what? Lower vacancy formation energy, then you can have a higher vacancy concentration vacancy, right? And regarding to the atomic jumping process, don't forget the mobility of the atoms, diffusing atom will be proportion with the exponential to negative migration energy divided by kT. So if you have a lower migration energy or higher temperature, then the mobility of a diffusing atom will be higher. So there are two criteria, right? So means first of all, you need to have a vacancy nearby, then the atom need to have sufficient energy to make a successful jump. So this times this, you need to satisfy these two criteria. So for sure, the diffusivity of the diffusing atom through vacancy-mediated mechanism will be proportional with exponential to negative energy divided by kT. The energy will be included the vacancy formation energy and migration energy, right? So this two energy, some people also call it as a activation energy of this diffusing atom through vacancy mechanism. So it will be the sum of a vacancy formation energy and atomic migration energy. Okay, so the other thing is some people probably were curious about let me draw something. The term here H. H turns out is enthalpy. Yes, here is enthalpy. But some people probably were curious about the E, energy. Or G gives free energy. Sometimes it will show in energy or gives free energy. So what's the relationship between the energy and the enthalpy? I would say G equals to energy equals to enthalpy minus temperature times entropy. So exponential minus divided by kT. The energy usually we talk about is gives free energy. So if you put here, let me change the color. Put this to substitute here. What you get? You will get the first term will be you will get the H divided by kT, right? It's the same we show here, right? The same we show here, right? And the second term would be you also have minus positive, and T you deleted T, so you got the S times the K. Actually, you got this term and this term, right? But we only show the but here we only show the temperature dependent term. Yes, this is a point. So where are the others? This term actually be put inside the D0. So the diffusivity always, as you mentioned before, diffusion is a temperature dependent term. So when you try to formulate or expression of diffusivity, usually we'll separate the temperature independent term and temperature dependent term here. So the entropy term, exponential to entropy term, actually is put at D0. So the one you show when we got the expression of diffusivity, the temperature dependent term here, you only have enthalpy here. But don't forget, it gives total energy here, okay? Okay, so now, okay. So now you know if the diffusion is a vacancy-mediated diffusion process, then the diffusivity will be proportional with the exponential vacancy formation energy and atomic migration energy divided by kT, right? So we are going to use this relationship and give you some case to show you how to how to derive these results and what's D0. Okay, this is quite important, right? Show you how to derive these results by using the previous results you derive about the diffusivity. So now what we have here is we have a vacancy-mediated self-diffusion mechanism, and crystal structure materials we have is the crystal structure of material we have is FCC. And this result diffusivity equals to 6 gamma mean square jump distance times F. This is a result we derive from section 1, right? Okay, and first of all, we know it is FCC and it's vacancy mediated. So I will draw the FCC here. So what's the FCC? We draw two unit cell of FCC. We got the 8 atoms at the corner and 6 atoms at the face. We call it FCC, right? Okay, then because it's a vacancy mediated, so I use a cross to label the vacancy we have in FCC. And don't forget, it's a vacancy mediated. The diffusion process here for sure will be, as long as you indicate, you point out the site of vacancy, so the diffusion mechanism for sure can be, the atoms for sure will be exchanged or jump into the nearby or neighboring vacancy to allow these diffusing atoms diffuse, right, through these materials. So this is what we call the vacancy-mediated diffusion process. Okay, so the purpose here is we want to show you what's the D0, show the diffusivity in the vacancy-mediated diffusion is expressed like this, and identify what's the D0 and also identify the delta H. Okay, so we start from here. So don't forget the diffusivity equals to this, right? So gamma total jump rate related to the possible jump directions times the gamma prime. So what's the possible jump directions? So first of all, you need to see, I already have a vacancy here. So the vacancy can jump to the possible jump directions of this vacancy equals to 12, right? Can be jumped to the face center on the top portion, H, and the bottom face center. So the Z equals to 12. And regarding to the small r is distance of the nearest atom. This atom jump to, as I mentioned, the jump distance for sure is the nearest jump distance. You cannot consider this one is longer than this one. For sure, it's the nearest atom. So we got the distance will be a divided by 2 square plus a divided by 2 square and take the root on this sum, right? So you got the small r. This small r equals to square root of 2 divided by 2a. And all directions small r the same, right, for these 12 atoms. So now we know the small r and know the z is 12, right? And for the vacancy, so now we try to formulate 2 parts of the atom. The first one is we call the diffusivity of the atom. We choose different point of view. The first one is atom's point of view, and the second one is the vacancy point of view. So we call the D star for the diffusing atom and the DV for the vacancy. Okay. And now I just want to label one thing. I will put the XB here. I hope you can end the XB here. Okay, I will explain this later. Okay, so regarding to the diffusivity of the atom, if I talk about this diffusivity of the atom, the first thing come up from your mind will be copy this result. It will be a 6, right? And Z gamma prime small r mean square jump distance times F, right? So if you write it down, it will be like, let me write down. will be the 12 times the gamma prime. Small r, I just copy this results is be right, small r square times f and divided by 6. It turns out probably you will just directly copy this one for the diffusing atoms. But is it correct? This is the diffusivity of the atom followed by this based on this equation, right? But the result is not correct. Why? You still miss one thing. The vacancy mediated what you need. The atom need to have a vacancy nearby, right? But this diffusivity haven't considered these conditions, so you need to times xv. Because you need to have a vacancy nearby, then the diffusivity, the atoms can diffuse. So I will suggest you to put the xv here. Okay? Okay, so based on this, we know the result will be xv gamma. Okay, so I put the a here. So let me write down. This is so put the a here. Okay, so if you try to arrange this one, you got the xv gamma a prime a squared times f. Okay, so be sure like this. And because why you need to xv? Because it lists for the atoms, diffusing atoms in FCC, it is correlated jumps. So and will be related with vacancy concentration. This is you successfully get the diffusivity of diffusing atoms in FCC. But when we switch the point of view from vacancy, so the diffusivity of the vacancy also copy these results. You got these results, right? The same, but we don't have xv because vacancy can go to anywhere. So we directly copy these results. So you just substitute. You don't need to consider this one. You just copy these results to here. The gamma v, so you also have 12. Because the vacancy can move to 12 directions, 12 gamma v prime r is used the same because the distance between this two lists and this two lists are the same, right? And you got these results. And for the vacancy part, vacancy, the f for vacancy can go anywhere. It's nothing related. The jumps is nothing related to previous one or next one. So f equals to 1. So we got this result, and f equals to 1. So we got this is diffusivity of the vacancy equals to gamma v prime a squared. Okay. Oh, next, some people probably will ask, yes, but f here because it's correlated jumps of the diffusing atoms, so we don't know the f, but for sure f is not equals to 1, so we leave the f here. Okay, so next, xv here, and the gamma a prime, you can express like gamma v prime a squared f. Okay, so here we know the relationship between the diffusivity of the atom and diffusivity of the vacancy in these structures. xv gamma v prime a squared belongs to dv times f. Okay, so here we know that. Oh, some people probably will gamma a prime will be equals to gamma v prime because the same star story, right? And so here you know that this information tell you this relationship tell you very important information. Here is diffusivity D star of the diffusing atom and diffusivity of vacancy. Which one is larger? Much larger? For sure, it's a diffusivity of vacancy, right? Because XV usually will be very small, will be like a 10 to minus 4 to 10 to minus 8. It's quite small, but you times dV equals to D star. So you know dV is much larger than D star by several orders. Okay? And as you know, the vacancy, atomic fraction for vacancy is quite small, right? Okay. And if you want to know, it's like 10 to minus 4 to 10 to minus 8, something, depends on different materials. Okay, so, but don't forget the purpose here. We want to show people what's the diffusivity, what's the D star as a function of temperature and also D0, right? So let's decouple this stuff. What's XV? We assume it is in the thermal equilibrium conditions. So XV will be equals to XV under the equilibrium condition. So will be equals to vacancy formation energy divided by KT, and G will be equals to H minus TS. So we separate into temperature independent term and temperature dependent term. Okay, so we rewrote this star XV, show here. And dV, what's the dV? dV equals to gamma V prime A squared. Gamma V prime expressed like this. So we got gamma V prime and A squared here. Also temperature independent term, dependent term here. And F, also F here. So after arrangement or organize them, you separate this term as a temperature independent term as a D0s. And the second is a temperature dependent term here. And in your textbook, it used E to represent the sum of the enthalpy. Here is included the formation energy and migration energy. Okay. And we also know the D0 star is related with the correlation factor, lattice constant, enthalpy term, and the mu. Okay. And don't forget, this is related with the bond strength and reduced mass. We showed this in previous slide, right? Okay, so next question I'm going to ask you would be, do we have chance to know, to measure, to design experiments to measure or to determine the vacancy formation energy and also the vacancy migration energy? How to do that?